well, I think we'll start without further ado, just a short reminder, it's 8 minutes talk and 4 minutes for questions, roughly speaking. So it is my pleasure to begin with the first talk, which will be given by Qi Tang, and it's a paper together with Stefan Kiefer about approximate by simulation minimization. So please, Qi.
Okay, let me share my screen. Okay, so hello everyone, my name is Qi. You can see my slides, right? Yeah, so this is, I'm a postdoc researcher at the University of Liverpool, and the paper I'm presenting today is approximate by simulation minimization, which is joint work with Professor Stefan Kiefer from the University of Oxford. So the model of interest in our paper is labeled Markov chains. So on this slide, we have an example LMC labeled Markov chain. Each state has a label, and the labels are represented by the colors of the states. So from each state, there is a probability distribution over the successor states. So for example, from the top orange state, with probability 1/3, it goes to S1, and with the remaining probability, it goes to T1. And we can soon detect the symmetry between the left part and the right part. So in probabilistic model checking, to tackle the state space explosion problem, we will compute the exact quotient of the system, that is to minimize the system. If we apply this algorithm to compute the exact quotient of this LMC on the slide, we will end up with a system with just 3 states. Now see that we are given another LMC, which is very similar to the previous LMC, but just the probabilities differ a little bit on the right-hand side. So by this small positive number, epsilon. But no matter how small this epsilon is, as long as it is positive, then S1 and T1 are no longer probabilistic by similar. So if we compute the exact quotient of this system, again, we cannot merge any states in this LMC. So that we will just end up with the original LMC with 5 states. So this leads to our goal, which is that we, because in practice, sometimes we are given LMCs with probabilities not known exactly. For example, this graph shows that this M we have here, we don't know the probabilities exactly. But all we have is another LMC M prime, such that the probabilities might be perturbed, or we obtain the probabilities by, for example, sampling. But in such cases, we still would like to compute an approximate quotient. We call it Q. And we would like that Q, the behavior of this approximate quotient Q, has similar behavior with the original system M. And also we would like that this Q, the size of Q is small. The state space of this approximate quotient is small. So not too bigger and not much bigger than the exact quotient of the original system. So let me give you the formal definition of approximate quotient. So given an LMC and the non-negative number epsilon, and LMC Q is an epsilon quotient of M if only if there is another LMC M prime with the same state space, the same labels, and the same labeling function, such that Q is the exact quotient of M prime. And we require that the probability transition function tau prime of M prime, that the successor state, the probability distribution over the successor states in M and M prime should have small L1 distance that is bounded by epsilon for all states. So it is very natural to ask the question. So here, because we don't restrict this tau prime, so this tau prime is not unique, the transition probability function. So we might have multiple epsilon quotients of an LMCM. So it is very natural to ask whether there exists optimal epsilon quotients among all these epsilon quotients of M. I mean, optimal is with respect to the number of states, the size of the state space. So, but as the next theorem suggests, even if we fix a positive integer k, the problem whether there exists an epsilon quotient of M of size k is NP complete. So it is unlikely that we will have an efficient algorithm or polynomial algorithm to compute such optimal epsilon quotient. So in our paper, we will not aim for computing such optimal epsilon quotient. Instead, we have a polynomial algorithm to compute an epsilon quotient of reasonable size. So in this talk, I will not talk about the details of this our polynomial algorithm. We will rather treat it as a black box. I will show you like how we apply this algorithm. But let me first show you a nice property of our epsilon quotients. So if it is very simple, so M2 is an epsilon 1 quotient of M1. And if M3 is epsilon 2 quotient of M2, then then we can add up these two numbers, epsilon 1 and epsilon 2. And we have that M3 is an epsilon 1 plus epsilon 2 quotient of M1. So we are given this M prime with perhaps perturbed probabilities. Then what we do is we first compute exact quotient. We call it Q0. Then we apply our polynomial algorithm, this black box, and we get an approximate quotient Q1. Then we apply our black box again to get another approximate quotient until we can no longer reduce the state space. So at the end, we get Qi. So if we know that each approximate quotient Qi is an epsilon quotient of the previous approximate quotient Qi minus 1 for all I, then by using this additivity property, this lemma, we have that Qi is an I times epsilon quotient of M prime. So this is how we apply our black box algorithm. And also in our paper, we do a lot of experiments. So what we do is we take an LMC from the model checker prism. We compute the exact quotient using the well-known algorithm. And then we get an LMC M prime by perturb the probabilities, transition probabilities of this LMC M. Then we apply our process to compute a sequence of approximate quotients. Then we compare the size of the final quotient Qi and the size of the exact quotient of the original system. So in this experiment, we have two parameters to tune. One is this perturbation error. We added to the transition probabilities of the LMC. And the other one is this a parameter we give to this black box algorithm, which we call it compression parameter. So for we find that from our experimental results, in most of the cases, if we set this compression parameter, which is given to our black box algorithm appropriately, then which means that it is a little bit bigger than the perturbation error that we used to perturb the original LMC, then in most cases, the size of the final approximate quotient will have the same or similar size as the exact quotient of the original system. And for more details of the algorithm, our polynomial algorithm, and for more experimental results, we will refer you to my video on YouTube and also our paper. Thank you for listening.
Thank you, Chi. Any questions? Is there? I'm not sure if I can. Just please unmute yourself and start talking if you have a question.
So my question is that the motivation of this problem is not exactly clear. So it started off saying that you don't know the original automaton. and you know a different automaton which might have a definite perturbation, which might be some epsilon. So you know a different automaton which has a slight perturbation, which is known, maybe some epsilon, right?
Mm-hmm.
And then you operate under that, and you try to get you try to find the quotient, assuming that there's a perturbation, and then compare it with the quotient of the intended automaton.
Mm-hmm.
But in general, how do you know what should be the epsilon? I mean, you have an automaton, but how do you estimate what the epsilon should be? How much is the perturbation?
Yeah, so for example, if this transition probabilities are obtained by sampling, then we will have like with high probability that there is some L1 distance between the transition probability distribution over the over the states. Then still we can we can get that with high probability that the approximate quotient and we get this approximate quotient.
Okay. I thought the perturbation was the maximal distance from the intended transition values, right? The epsilon. It was. Oh, I mean, I see. You mean those probabilities? Okay.
Yeah.
Okay. Thanks.
I think there's another question from Shibashish. So please. Go ahead.
Yeah. So thanks for the very nice talk. So you mentioned that in your experiments, what you found is that this approximate quotient for many of your experimental benchmarks, the size are more or less similar with the actual exact quotient and this approximate quotient. So could you give some idea of like the size of the Markov chains that you started with in your benchmark? Like how big were these Markov chains?
So the original LMC,
the epsilon value that you used in your perturbations.
Oh yeah, sure. So the original LMC it can be very big, like with thousands of states or thousands more than thousands of transitions, hundreds of thousands of transitions. Mm-hmm. Then we vary this perturbation error from quite small, like 0.001, then until like 0.1. Mm-hmm. Then we also like there's another parameter which is the input parameter to our algorithm. Then we also vary that parameter from very small to a little bit big to 0.1.
Okay, so for most of these parameters, you found that like the sizes of the two quotients are like the approximate ones and the exact ones are pretty similar, like they're close to each other.
For most of the results, if this second parameter, that is the compression parameter given to the algorithm, is a little bit bigger than the perturbation error,
okay,
we will have that, like the size will be the same or similar.
Okay, thanks.
So thank Chi again, and let's. Thank you very much. And let's move to the next talk, which I guess will be given by Rasmus. Is that? So the next talk will be.
That is correct.
Given by Rasmus Ibsen Jensen about quantitative verification on product graphs of small trees. So please go ahead, Rasmus. Connect.
Can people see my screen? People can see my screen. Excellent. I assume so at least. Otherwise, please tell me. So this is a bit of a mouthful of title. It's based on joint work with Christian Ducatelli at IC Austria and Andreas Pomegianis at Aarhus University in Denmark, and myself, I'm at the University of Liverpool in the UK. So what results do we have in the paper? Well, we show improvement, a polynomial factor improvements for product graphs of various problems, especially when they have constant or small tree-width graphs. So if you take two small tree-width graphs, for instance, from mean pair, and take the product of these, then we can solve a mean pair faster, as in find the smallest cycle in the system. We can solve the similarly distance faster, but not time to introduce here in the talk. But basically, if you don't know what it is, just think of it as distances like shortest path, but with negative weights. And we can solve the initial fitted problem faster. That is, find the smallest number so that is a cycle, so that the prefix sum of the numbers are non-negative. And basically other kinds of problems, as long as they are on product graphs of two constant or small trivial graphs. So yeah, we get some polynomial factor improvements. In the first case, we got a linear improvement. In the second case, we got a small epsilon improvement. And in the last case, we got an n-to-the-third improvement. And this kind of problem shows up in the static analysis of concurrent programs. So basically, each of the small trivial graphs was one per program, and they are known to have constant trivet in many programs. So what we really do is we show how to, and this is sort of a notion for this small trivial graphs, how to do a better balanced trivet. So that the nodes in the subtree rule that any node that k in this tree has size binary tree definition has size n times a half plus 2 to the minus lambda to the k. If you think about it for a minute or two, you will see that the best you can do is n times a half to the k. So we have sort of exponentially small additive factor, additive term inside here in the before we take the experiment, and we end up with a trivet, which is then well, if it was constant before, it's linear in lambda afterwards, and generally if it's t before, it will be lambda times t afterwards. We also show that these balanced tree decompositions must lose a factor in trivet when you go from non-balanced to balanced. I'm not sure if this was known already. We have not been able to find it in the literature at least, but it might have been folklore already. So let me give you a definition of what these tree decompositions are. I'm going to go a bit fast because of time pressure here. So if you have a connected graph G and a tree decomposition is then a pair over this graph, where you have a set of bags B and a tree over this bags T, and each bag contains a set of nodes of the original graph. And what you must have is that for each edge in the original graph, there's a bag containing both endpoints. And for all nodes, the subtree containing just this one node is a connected subtree. So what we get is that the trivet of a tree decomposition, one of those things here is the maximum bag size -1. And the trivet of a graph is the smallest trivet of any of his tree decompositions. So you might have many tree decompositions for the same graph, but you take the one with the smallest trivet, and that gives you the trivet of the graph. For instance, it's always a tree decomposition if you just take all nodes and put them into a bag, and let that be the tree order. So for instance, if you have this graph here, we can end up with this well, tree decomposition over on the right. I'm not sure if people can actually see it with the pictures here, but can I move it around? Yes. So the key here is that even though the original graph doesn't really look like a tree, it turns out to be, in a sense, maybe tree-like, because trivet 1 is a tree, and here we have trivet 2, as in we have the maximum bag size, which is 3, -1, that's 2. So even though this graph doesn't look especially much like a tree, it turns out to be very tree-like in some sense. And that let us do things faster. And again, as I said, many programming languages ensures that the tree decomposition of the control flow graph has constant trivet. So what properties can we assume about this kind of thing? Well, classically speaking, we can assume that the number of bags is the most linear in the number of nodes. We can assume that the tree decomposition is binary. And it's also known that we can assume that it's balanced, as in the height is log n. So these two, you'll find it in most introductory textbooks, text on trivet. The last one doesn't show up in introductory text for some reasons, but I feel it's not very natural because, well, we will know well that it's not nice to have balanced trees. So on. Part of the answer to why the first two shows up and the last one doesn't is that the first two are free in the sense that you can construct a tree decomposition with the same tribute, but having these two properties. The last one, as I mentioned earlier, it does cost something to do this. And again, I suspect it might be folklore, but I couldn't find that citation. And at least we do show it for me. So what the classic results does, and there is quite a few of them, they end up with a tree decomposition that has height 2 log n when you convert it into binary trees. So the problem is that this 2 ends up destroying all our improvements in the state of the art. So that's not really great. So we will try to make it better balanced by basically having a lower height for the tree decomposition. So what we do, well, the classical ones, as I already mentioned, ensures that every time you go 2 levels down, you have the number of nodes below you. So at that k, you have a size of the subtree below you as most as n times 2 to the minus k divided by 2, and the tribute is well, a constant times the original tribute. So we had a previous paper on it, and this is part of the motivations of this paper, where we did it with basically just a linear scaling of the two. So if you had a factor of lambda more tribute, you get n times a half plus 1 over lambda to the minus k for the number of nodes under the subtree at depth k. So, well, that was a pretty nice paper, and we then found out that we had, in some sense, messed it up because, well, we can do this exponentially better, and that was sort of by one of the reasons why we moved this paper. So what we managed to do was bring it from this polynomial down to an exponential improvement over what we had before. So for any lambda, we get a tree decomposition which has nodes below the k nodes of n times a half plus 2 to the minus delta to the k. So again, it's going from a polynomial to an exponentially small number. And that was basically my talk. Thank you.
Thank you, Rasmus. Are there any questions? So please raise your hand or unmute yourself. I have a silly question, I guess. Do you have similar results for creek width?
No, we do not. We only tried it for tree decompositions. As in the key thing is that when you construct a tree decomposition of a product graph, you end up basically. So if you have 2 tree decompositions, you end up constructing it like this. So it's of 4 times as many nodes at level 2, in some sense, and these end up depending on the subtrees under the original one. It's not the case for click as far as I know. So the reason why it's not necessary here is well, it's sort of close up.
Okay. Thank you. Any other questions? Okay, if not, let's thank Rasmus once again, and let's move on to the next talk, which will be given by Benjamin Borel about determinacy in concurrent graph games. So please.
Yes, can you see my slides?
Yes, they're good. Thank you.
Thanks. So, hello. My name is Benjamin Bordet, and this is a joint work with Patricia Bouillet and Stéphane Leroux. And this consists in the study of local to global determinacy in concurrent graph games. So before looking at concurrent graph games, let's take a quick look at turn-based graph games. So a turn-based game consists in a graph where two players, player A and player B, are going to play sequentially. That is, at each state, exactly one player is going to choose the next state, thus inducing an infinite sequence of states. So in this example, we have that player A is going to play in two states, where player B is going to play in two states. And then we add what is called a winning condition. That is, a condition stating at which player wins as a function of the sequence of states in. So for instance, in that case, we have that player A wins if the state Q equal is reached, and otherwise player B wins. And we can see that in this example, player B has a way to ensure winning by playing those green arrows here. And so in that case, we say that player B has a winning strategy, deterministic one. Let's move on now to concurrent games. So a concurrent game also consists in a graph where also two players, player A and player B, are going to play. But now they don't play sequentially, they play concurrently. That is, at each state, both of the players are going to choose an action, and as a result, a next state is going to be reached. So for instance, at the set Q0 here, player A is going to choose a row, player B is going to choose a column, and as a result, as the Q equals Q different is going to be reached. We can also add a winning condition here. So again, player A wins if Q equal is reached, and otherwise player B wins. But we can see that in this example, neither of the players has a way to ensure winning, because if they play the same thing, player A wins, and if they play something different, player B wins. So in that case, we have that no player has a winning strategy. So if we consider the notion of determinacy, which encompasses the fact that either of the players has a winning strategy, we have that turn-based graph games are determined for any Borel winning set, which encompasses a very large class of winning objective, winning set. However, in concurrent graph games, where very simple games are not determined, such as the games that I have showed before. And our goal was to find a large class of determined concurrent games. And the way that we did that is we looked at concurrent games, such as the ones that we have seen so far, and we looked at the local interaction in those concurrent games. So, for instance, the local interaction at state Q0 here is a bidimensional tables depicting the interaction of both players, which can be rewritten like that up to a renaming of the outcomes. And in fact, this game form, this local interaction is in fact what is called a game form, which basically is a bidimensional table where player A chooses a row and player B chooses a column. And the variables here that appear, so X and Y and Z, are called the outcomes of this game form. And we are going to see that, in fact, the game forms that we want to have in the local interaction of concurrent games are, for instance, the one at the bottom, whereas the one on the top are the game form that we want to avoid. And to realize that, we are going to build a game from a game form. That is, we are going to have a map from the set of outcomes to WA and WB. WA meaning player A wins, and WE meaning WB meaning that player B wins. And we have, for instance, that in this situation, we have a row of WA, and this means that this is a winning row for player A, because player A has a way to ensure reaching WA regardless of the action of player B. Similarly, a column of WB is a winning column for player B, whereas there is no winner if there is no row of WA and no column of WB. And this is basically a situation that we want to avoid. So overall, we are going to consider determined game forms, that is game forms such that for all map from the set of outcomes to WA, WB, there is either a row of WA or a column of WB. That we are basically saying that either player A or player B wins. So for instance, the game form that was in the concurrent games that we have seen initially is not determined, and that is the witness. This game form is also not determined. For instance, that's a witness. However, this game form is determined. For instance, in that game, player A wins, in that game, player B wins, etc. We could list all such game, and we could see that either there is a row of WA or a column of WB. And then what we are doing is we are considering locally determined concurrent games, that is, games where concurrent games where all local interactions are determined, and then we are able to transfer determinacy results from turn-based games to locally determined concurrent games. And so let's look at the idea quickly. So we consider a locally determined concurrent game such as this one. So the local interaction at state Q0 is a determined game form. And we are going to sequentialize this game like this. So we are going to make player A plays first at Q0, and then player B is going to respond, and then it's again the turn of player A. So the sequential version of a turn-based game, of a concurrent game, is in fact a turn-based games. And we can see that in the sequential version T, player A has basically the same kind of, the same amount of information because she doesn't know what player B is going to play. However, player B has more information because she knows what the action of player A is. And then what we're going to do is we're going to translate the strategies from the turn-based game T to the concurrent game C. And basically, we are able to translate winning strategies. So for player A, we basically take the same strategy because they have the same amount of information. However, for player B, it's more difficult because in the turn-based games, player B has more information. And so this part uses the local determinacy assumption on the concurrent games that we have. And overall, what we obtain is that locally determined concurrent game C is determined if only if its sequential version T is, whereas T is in fact a turn-based games. So as an application, for instance, we could have that from this theorem, recall that we have that turn-based graph games are determined for any Borel winning set, whereas arbitrary concurrent games are not determined for very simple games. However, with our theorem and the already existing theorem on turn-based games, we can transfer determinacy results from turn-based games to locally determined concurrent graph games that are determined for any Borel winning set. And finally, a few concluding remarks. So note that the fact to having local interactions is a sufficient condition to ensure determinacy. It is also somehow a necessary one in the sense that from any game form or local interaction that is not determined, we can build a concurrent game from it that is not determined. Furthermore, this transfer works for a state space that is either finite or infinite. The strategy transfers that we have also preserve memory, so positional strategy and finite memory strategies are preserved. And finally, this also holds in a stochastic setting. So if the outcome of a local interaction is not a state, but a distribution of the states, and then we don't talk about winning strategies, but rather optimal strategies, and we can also transfer those strategies as long as they are deterministic. Okay, thank you.
Thank you very much, Benjamin. So please, any questions?
I have one question.
Yeah.
If you have given such a concurrent game, how do you know if it's locally determined?
Yeah, so indeed, that's the result. It talks more about a safe way to build concurrent game, I would say, in the sense that basically we are allowed more than only turn-based interactions in which only one player plays, but we are also allowed determined local interactions. But and so this ensures that the concurrent games that we are building will ensure nice properties, just like turn-based games would be in terms of winning strategies. However, indeed, when you are given a turn-based a concurrent game, it's, well, you would have to look at every local interaction to check that they are determined, which is itself not very easy. So yeah, I would say it's more of a result useful to build a nice concurrent game instead of checking that concurrent games ensure this property.
Okay, and but is it decidable if it's locally determined? Is it just complicated, or is it even undecidable?
So to check that a game form in itself is determined, this can be done. This is a decision problem in CoNP, in fact, because you can just guess evaluation and check that it is not determined. So overall, you can do it. And for an arbitrary concurrent games, well, yeah, you can just enumerate every local interaction that appears in that game and check that it is determined. So no, it is possible, but I would say it's not very practical. I would say it's more useful to build a concurrent way in such way that every local interaction appearing are determined by construction, but you can obviously check that it holds. But it's just that if you are given an arbitrary concurrent game, it would be quite unlikely that every local interaction appearing are determined.
Any other questions? Let's check. Okay, so if not,
I had one question.
Sorry, I missed that. Please go ahead.
Yes. What if we just knew that all local interactions sort of was determined for the relevant ones, as in some of the local interactions mappings you're looking at might not be relevant for a certain game. For instance, we might know we lose if we go in, as in we will surely lose if we go into a specific entry. And can we use that to make it simpler, or if we somehow knew already that all the local interactions will then satisfy this determinacy?
Yeah, so of course, if every local interaction is determined, everything works fine. It may be that in a concurrent game where some local interactions are not determined, it's also fine if, for instance, such local interactions are not really reachable from the initial state in some way, like one of the players will ensure not reaching that, otherwise he is sure to win, to lose, obviously. But that would require a very careful analysis on the concurrent games that you are given. And I guess if you are able to do that in some way, you would be able to directly solve the concurrent games that you are looking at directly, without having to look at the local interactions, I would say. But okay, it would be something to look at.
Any other questions? Okay, if not, then let's thank Benjamin again. And now, Sarah, the floor is yours for the last talk. So the last talk will be given by Sarah Winter. Please. The last talk of FSTTCS. There's also the invited talk in shortly.
Yeah, you can see my slides and hear me. Okay, great. So I present to you joint work with Emmanuel Filliot about synthesizing computable functions from rational specifications over infinite words. So the motivation of this is program synthesis, where you have given a specification and you want to synthesize an implementation that satisfies the specification. What does it mean? So a specification is simply a relation between inputs and outputs. For one input, there might be several valid outputs, and an implementation is a function that is has the same domain as the specification. And every value selected by the function, this pair is part of the specification. So here's a little example. This is a specification of a traffic light. Given a logic, a traffic light is green infinitely often. Once it is red, it cannot become green immediately. And before it becomes green, there is some yellow phase. So on the right-hand side, we have a program. It's the light is green for 120 seconds, then it goes to red. The red phase is 30 seconds. Then we have a 5-second green phase, and then it goes to green again. So while this is not the safest traffic light going from green to red, it satisfies the specification. So, and this is a very general problem formulation, so it is undecidable in general, depending on what kinds of specifications and implementation one chooses. And here in this talk, I'm interested to synthesize stream processing programs from binary relations of infinite words. Let's take a look at a simple example. Here we have a specification from infinite words that start with a finite prefix over A and B. Then we have a special letter X, which is either a big A or a big B. And then we have an infinite reminder also made up out of A and B. And the output should simply start with the special letter X we have seen, and then have also this finite prefix U, and then a reminder of A's and B's, and we don't care how it looks like. So in this specification, we can implement it by a program. We simply have to read and store the input until we see our special letter A and B. Then we can output our special letter and our stored input, and then, for example, copy the remainder of the input letter by letter. Okay, so now let me be a bit more formal what we mean by stream processing programs. We mean programs that are computable functions by a deterministic Turing machine. What does it mean? A partial function from infinite words to infinite words is computable if there exists a deterministic Turing machine that has 3 tapes. We have a one-directional read-only input tape. We have a bidirectional working tape that can be read and write on, and we have a one-directional output tape. And we say that the function is computable if we have such a deterministic Turing machine, such that when on the input tape there is an input which is from the domain of the function, then whenever the Turing machine reads longer and longer prefixes of this input, then on the output tape we have longer and longer prefixes of the function value. And whenever the input tape holds something which is not part of the domain of the function, we do not care how the Turing machine behaves on this input. Okay, so I've used my same slides as for the long talk, so I'm going to skip something. Yeah, what kind of specifications am I interested in this talk? Here are specifications that are omega rational relations. Omega rational relations are given by non-deterministic transducers with, for example, a parity acceptance condition. Here, this Turing machine recognizes the specification I've shown you before. The first transition is determined by the output, by the first output letter, which is either the special A or special B. Then here we copy the input letter by letter. And then in the input, we are looking either for the special A or the special B. And in the end, we don't care how, which input is combined with which output. And here's a simpler specification. Here we can decide if we want to replace A's in the input with 1 A or with 2 A's, and B's are simply replaced by B's. So in general, the transitions are pairs of words. The first component is the input word, and the second component is the output word. Okay, so I have to start with a negative result. It's undecidable whether we can synthesize a computable function from an omega rational relation. And this result is not very surprising because it's an easy adaptation from the finite word setting, where it was shown that it's undecidable whether one can synthesize a sequential function from a rational relation. But we have a positive result. We have a game reduction. If our rational relation is given by a transducer, then from this transducer, we can construct a game with an omega regular winning condition. And if one player, Eve, has a winning strategy in this game, then we can synthesize a computable function from the relation. So I'm going to skip how the game looks like. But we also have for the game a completeness condition such that this game reduction is not only sum, but also complete. It is a structural condition on the transducers. I don't want to go into detail now. The condition we have might sound rather arbitrary, but by default, it includes very well-known and important classes of rational relations. For example, every omega automatic relation satisfies this property. Omega automatic relations are the relations that are given by letter-to-letter transducers. And also an even bigger class has this structural property, deterministic rational relations. And if we have given a relation given by a transducer that satisfies our property, then the problem of deciding whether a computable function can be synthesized is X time complete. Okay, so this I'm gonna skip. And then Well, we might ask, okay, computable function means Turing computable, and the power of Turing machines is very large. So is it even necessary for our implementations to use the whole computing power that Turing machines offer? And it turns out this is not even necessary. Whenever we can synthesize a computable function from these relations, then this implementation can also be done by deterministic two-way transducers. So here's a little example. This is the specification I've shown you before, where we have to wait for the special letter that determines how our output should look like. This function here is the implementation I've shown you before, where we simply output the special letter and then copy the prefix and the remainder. And how could a deterministic two-way transducer do it? A deterministic two-way transducer can go to the right in the input, produce nothing until it sees the special letter, then produce nothing and go back to the beginning, then produce the special letter, and then can simply copy the input letter by letter. And this is an implementation of this specification. Okay, so this I'm gonna skip, which already brings me to my summary. So in general, it is undecidable whether one can synthesize computable functions from omega rational relations. We have an incomplete but sound reduction to an omega regular game. It is complete for large subclasses of rational relations, which includes the important class of omega automatic relations. If we can synthesize a computable function, it suffices to use deterministic two-way transducers for the implementations. And when the specification has total domain, which means every input is a valid input, then it even satisfies to use one-way transducers for the implementations. Okay, thank you.
Thank you very much, Sarah. So please, I open for questions. I have a question about the two-way transducers are enough.
Mm-hmm.
Could it be made into an exact characterization in the sense that two-way transducers are exactly what you need to synthesize, to solve a certain synthesis problem? Maybe the one that you have, maybe a similar one, I don't know.
Yes, so there is something which is not by me, but that if you take the intersection of rational functions and computable functions, that this class of functions you get is included in the set of two-way deterministic transducer computable functions. So I think there is some general connection, yes.
Thank you. Any other questions? Well, if not, let's thank Sarah and all the speakers again. Thank you very much. And this concludes our contributed talks. So thanks to all the speakers and to all the participants for coming in and asking nice questions. And well, see you at the invited talk shortly. Bye. Thank you.